Hello, and thanks for listening in. In this video, we will show how to construct a theory of the classical electron with Coulomb fields that radiate at the speed of light. Although this represents a violation of energy conservation on a cosmic scale, we like it because it has promise for generating an expanding universe loaded with dark energy. The basic program is this. While acceleration fields are oscillations of the electromagnetic field transverse to the direction of motion, we will show that velocity fields can be associated with oscillations parallel to the direction of motion. This unifies the velocity and acceleration fields of the electron as particle radiation fields and characterizes the velocity fields as emitters of electromagnetic sound waves. For reference, we will refer to energy in the velocity fields as vacuum energy. Generating momentum flux velocity fields is easily accomplished by multiplying the Coulomb fields by a fundamental surface charge density. We assume that the presence of momentum flux in the fields does nothing to inhibit the fields from exerting forces on other charged particles. In other words, a theory of radiating Coulomb fields is nothing more than a symmetry operation that leaves the Coulomb fields invariant. The CPT theorem is still valid for radiating Coulomb fields, since the action of the force has nothing to do with the radiative property of the force that's being introduced. Maxwell's equations are still valid for the radiation-based electron theory, but they have a somewhat different appearance, including sources which are force densities instead of charge densities. Of course, radiating Coulomb fields still allow for momentum and energy flux calculated from the Poynting vector, which must be written in terms of the flux fields. Here, the constant mu sub e is exactly the outward pressure tending to explode the classical particle. We can include radiating Coulomb fields into theoretical physics by introducing only a slight modification to the 1905 postulates. The postulate of relativity remains the same, but the constancy of light postulate must be altered to reference all possible radiation fields. This is mainly just a generalization of the Einstein postulate. A theory of radiating Coulomb fields cannot be established by working in the Lorentz gauge. Instead, it will be necessary to apply the covariant vacuum gauge condition. Any set of potentials which satisfies this first-order differential equation may be referred to as vacuum gauge potentials. The most important set of vacuum gauge potentials for the classical electron are the light-like null potentials, where R nu is the vector from the retarded position of the charge to the present time field point. We note that the radial nature of vacuum gauge potentials are indicative of their ability to describe the physics of a single charged particle. An interesting interpretation of the vacuum gauge condition is the following. In the rest frame, suppose we assign a complex exponential to the light-like vacuum gauge potentials. Vector and scalar potentials are now traveling spherical waves. We don't know the frequency of these waves, but the phase, tau sub e, is just the classical electron radius divided by the speed of light. And we note that the vector potential functions to propagate longitudinal modes into the space-time. Remaining in the rest frame, we can calculate the fields from the potentials. For the classical particle, we see that the Coulomb field oscillates at the same frequency as the potentials. Of course, the magnetic field is still zero. Now, you may be surprised to learn that the traveling wave potentials and fields that we've calculated here still satisfy the vacuum gauge condition. You are also invited to show that the rest frame fields, now boxed in red, still satisfy all of Maxwell's equations, but with a modified definition of source current density. Still in the rest frame, let's combine the scalar and vector potentials in a way that produces a 1 over r squared energy flux field proportional to the electric field vector. A simple integral will then determine inertial vacuum power. This is a huge number on the order of 10 to the 10 watts, but it remains to be seen whether the radiated field energy has any mass equivalent. To make a covariant theory, we can easily build a rest frame momentum flux tensor by writing this antisymmetric matrix here. A Lorentz transformation will then produce the velocity field strength tensor multiplied by a fundamental surface charge density. This implies that the magnetic fields of the particle also carry momentum. A more sophisticated approach towards deriving a momentum flux field strength tensor begins by writing out the moving frame light-like vacuum gauge potentials. But we can write the vacuum gauge potentials as the sum of time-like and space-like components. A momentum flux tensor may then be established by commuting the time-like and space-like components, where one of the terms is complex conjugated. Finally, nothing has been said regarding acceleration fields in the vacuum gauge. Similar to the velocity fields, the vacuum gauge requires the acceleration fields to be carriers of momentum flux. In addition, the flux fields can be shown to satisfy their own set of Maxwell's equations, and we note here that unlike the Lorentz gauge, the acceleration fields require sources. However, these sources are still force densities. This leads to a generalization of the Poynting vector for accelerated motions of the particle. To close, we need to say a few words about gravity. We assume here that radiation in Coulomb fields will translate into additional radiation by stars. Even though the field radiates, the energy density surrounding a star will appear static, and this means we can use the Schwarzschild metric to determine curvature. Now let's write out the field equations, but this time requiring a source term d mu nu to account for the additional radiation. This source term features the constant epsilon, which measures the magnitude of the radiated energy density. We encourage anyone to determine how big epsilon can be before the space-time surrounding the star shows measurable differences to the well-known problem without the source. Thanks again for listening in, and have a great day.